am Sangeeta R, a third year ECE student. Today I am going to present my internship project titled EV ADAS System, a real-time electric vehicle dashboard using STM Loopil and PICSimLab. This project was completed as part of my Automotive Embedded Systems internship at Emertxe Information Technologies. Throughout this internship, I worked with STM32 programming, embedded C, UART Communication, PICSimLab Simulation, and Python dashboard development. Now I'll explain the complete project through this presentation. Let's move on to the next slide. Before I explain the project, I would like to briefly talk about my internship. This internship focused on automotive embedded systems. The main objective was to understand how embedded software is developed for modern electric vehicles. Instead of only learning theory, we were asked to develop a complete embedded project. During this process, I learned how different software tools work together and how real-time data can be monitored using embedded systems. This internship also improved a very great debugging skills, problem-solving ability, and confidence in handling real-world projects. Next, we can move about this. Next slide. The main objective of this project was to design and simulate an electric vehicle, that's the ADAS system. The system continuously monitors important vehicle parameters like speed, battery, state of charge, motor temperature, torque, and remaining range. Along with vehicle monitoring, the project also includes advanced driver assistance features such as forward collision warning, blind spot detection, and parking assistance. This is the dashboard that I have developed. So let's move to the next slide. This is about the tools I have used. This project required several software tools and each one had a specific purpose. I used STM32 Cube IDE for writing embedded C code, compiling the project, and debugging errors. The PICSimLab was used to simulate the STM32 Bluepill and the sensors without using physical hardware. The Python was used to build a real-time dashboard that displays all the vehicle parameters. VSPE was used to create virtual components for UART communication between PICSimLab and the Python dashboard. Together, these tools helped me complete the entire project in a simulated environment. Further going to the next slide. This is about the hardware components that I have used in the simulation environment. Even though this project was simulated, it follows the same hardware structure as a real embedded system. The main controller is the STM32 F1 series of Bluepill microcontroller. 3 HC-SR04 ultrasonic sensors are used to detect obstacles in the front, left, and right directions. Potentiometers are also used to simulate the accelerator input, that's the acceleration about that, and brake input, battery state of charge, and motor temperature. LEDs and a buzzer are also included to provide warning indications whenever any unsafe conditions is detected. Let's go on to the system architecture. This slide shows the overall working of the system. First, STM32 reads all the sensor values, then it processes the data to calculate speed, battery percentage, torque, remaining range, and other vehicle parameters. The ADAS module continuously checks for collision risks and blind spot conditions. Finally, the processed data is transmitted through UART communication to the Python dashboard where it is displayed in real time. Now, let's move on to the next slide. This is the system workflow. Now, let's explain the working of the project step by step. Initially, this STM32 reads all the sensor inputs. Using these inputs, it calculates various vehicle parameters like speed and all that I have already explained. Then after that, the ultrasonic sensor measures the distance of nearby obstacles from the front, right, and left. The ADAS algorithm checks whether an obstacle is too close and calculates the time to collision. If any dangerous condition is detected, The system generates an alert and displays it on the dashboard. And the advanced driver about the ADAS system, we can see this in the slide. In the slide, the ADAS driver assistance is one of the important parts of this project. Forward collision warning alerts the driver whenever an obstacle is detected very close to the front of the vehicle. Blind spot detection monitors both the left and right sides of the vehicle. And the parking assistant also helps the driver while parking by continuously measuring nearby obstacles. The system also classifies alerts into different priority levels for critical situations to save immediate attention. This is the dashboard where you can see from the left there is an obstacle and from the right too there is an obstacle. Let's move on to the next slide. This is the Python dashboard features. This is the Python dashboard developed for this project. You can see it on the right side. It displays all the important vehicle information in real time. The dashboard includes a digital speedometer, battery state of charge, motor temperature and remaining range, torque, and an ADAS bird eye view. That's from the top view. Whenever the STM32 sends new data through UART, the dashboard immediately updates all the values. This provides a clear and user-friendly interface for the monitoring the vehicle. Going to the next, that's the UART communication. This UART communication, the communication is between the STM32 and the Python dashboard that happens through UART. The UART baud rate is configured to be 115200 bits per second. This STM32 continuously sends vehicle parameters like speed, battery percentage, temperature, torque, and sensor distances. The Python dashboard receives these values through the virtual serial port and updates the real display in real time. This communication is one of the most important part of the project. And this is the code workspace of STM32 IDE. That picture we can see, in which we can see the various codes for main.c, fault.h and all. And I will explain all these at the end of our presentation. Let's move on to the next slide. It's about the challenges that I have faced during the development. I would also like to share some of the challenges. Initially, the ultrasonic sensor always showed the same value. There were several communication errors while writing the Emertxe code. Setting up your communication between PICSimLab and the Python dashboard was also very challenging. Sometimes the dashboard showed only demo values instead of my own sensor values. There were also comport conflicts and communication errors that took time to solve. Although these challenges were difficult, each problem helped me improve my debugging skills and understand the system much better. Let's see about the skills I gained or the learning outcomes. This internship helped me learn much more than just programming. I gained practical experience in embedded C programming, STM32, HAL programming, UART communication, Python programming, and PICSimLab Simulation. I also learned how different software modules work together in an embedded system. Most importantly, I understood that debugging is an essential part of engineering and patience is one of the most valuable skills while developing embedded systems. Finally, the results achieved. Finally, I was about to complete the project successfully. The STM32 reads all the sensor simulator values. UART communication worked successfully between PICSimLab and the Python dashboard. And the dashboard displays all the vehicle parameters in real time. The ADAS system correctly detects collision warnings and blind spot conditions. Overall, the project achieved all the major obstacles and objectives that were planned at the beginning of the internship. Now let's go through the pictures I have included in this presentation. Let's go from the start. You can see in this slide that this is the picture of command prompt that that's related to Python. This is the pathway for Python dashboard. And in this slide we can see the VSP3, that VSPE picture. Here I have connected my devices from COM1 to COM2. This is the virtual terminal. You can see all the values here. This is the Python, not STM32 IDE workspace. This is the dashboard. This is the workspace that's spare parts part of PICSimLab. You can see all the sensors and all here. The top three are ultrasonic sensors, and here on the bottom you can see the potentiometers. These are the LEDs, and this is a virtual terminal. Yes, this is one of the workspace of STM32 IDE. This is for cloud configuration. You can see this is blue pill, that board that we have used microcontroller blue pill board. This is pinout configuration side for in the workspace of STM32 IDE. This is the total PICSimLab thing that I have done. So okay, we have come to the end of the presentation, and at this time we can see the whole thing that I have done. That's we can see the demo and all, starting from the STM32 IDE. So this is the workspace. Now let's explain the firmware developed in STM32 IDE. The entire project was written in embedded C using STM32 HAL library. Initially, I configured the required peripherals such as GPIO, UART, ADC and timers using STM32 Cube Emmertxe, and then the generated project in STM32 Cube IDE. Inside the program, the microcontroller continuously reads the sensor values, simulator values like accelerator position and brake position, battery state of charge, motor temperature, and ultrasonic sensor distances. Based on these inputs, the firmware calculates the important vehicle parameters such as battery, speed, motor torque, battery percentage, and remaining everything, and also time to collision. After processing all the values, the STM32 transmits the telemetry through UART to Python dashboard. The firmware also continuously checks for collision conditions, blind spots, and fault conditions before sending the data. As you can see in this project Explorer side, in the include file folder, we can see ADAS.h, common.h, evcontrol.h, fault.h, main.h, and UART shell.h, ultrasonic.h. These are that supports the working of the entire code. And in the source file, you can see ADAS.c file, evcontrol.c file, fault.c file, main.c file. Then you can see UART shell.c file, that's for the UART communication, and ultrasonic.c file. You can see this is the EV dashboard IOC. Let's wait to look at that. It's loading now. Here you can see the pinout configuration and clock settings too. Let's wait for a few more seconds. Here it is. You can see the pinout configuration. Let's zoom in. You can see that we have marked for GPU pin out, pin in, ADC for everything. Timers too. Here's system core, analog, ADC, timers. This is the systematic view. You can see everything that we have connected for that, and it's the cloud configuration. Okay, let's move on to the PICSimLab workspace now. This is the blue pill, that microcontroller board that we are using for the simulation environment. This is the spare part side. Let's keep it here. Okay, now let's line this all. As you can see, these all are the potentiometers. We have 4 potentiometers connected to the various ports and pin PA0, PA1, these pins. Okay, first is the acceleration pedal, second is the brake pedal, and third is the SOC, fourth is for the motor temperature. This is the virtual terminal, and this one is the front ultrasonic sensor which detects front obstacles. This is the right side ultrasonic sensor which detects obstacles from the right. This is the left ultrasonic sensor. This is the buzzer. This one is for ultrasonic sensor related with the front one. This related to the left one, and this is related to the right. This is for fault. This is for the fault. As you can see, if motor temperature increases or decreases, it shows the fault values, its conditions, and the values now in the ultrasonic sensors are in collision condition, so that's why it has turned yellow. Let's move on to the now virtual terminal. Basically this yellow LED is for the alerts and all. Let me show the virtual terminal. This is the virtual terminal. Input output virtual terminal. You can see there is first one front distance. F is for the front, refers to the front distance, L for left distance, R for right distance, and TTC is time to collision. Now we have alarm, three alarms are taking place. Fault, we have 4 faults. 4 faults are the present. Now they can see this is speed, this SOC, and TRQ, the torque, temperature, choose temperature, and range, orange range. This the ACC acceleration, that value. This brake, we have currently 0 brake. As you can see here, we have currently 0 brake here. Wait, let me show you a while. Okay, here this is for the brake. It is 0. It is in 0 condition. Okay, now let's move to the this is spare parts. We can okay. List of the spare parts available inside PICSimLab. When I used to build my simulation, the potentiometers are also used here. Since I didn't use any physical hardware, the PICSimLab acted as my virtual development board. Here the STM32 blue pill is connected with different virtual components like potentiometers, ultrasonic sensors, LEDs, and the buzzer. Whenever change the potentiometer or move the obstacle, the STM32 immediately reads and updates the values and processes it just like a real embedded system. This is the spare part side. I can see everything here now that I have shown. The buzzer generates the alarm sounds during collision or fault situations. LEDs indicate different warning conditions that I have already explained. Then okay, what's next? I was able to test the complete project without using actual hardware, using this PICSimLab workspace. Now I have already explained the virtual terminal. In the virtual terminal, you can see all the values stored, and whenever the firmware executes, it continuously sends vehicle information such as speed, battery percentage, motor temperature, torque, and ultrasonic sensor distances. This terminal helps verify whether STM32 is transmitting the correct data before sending it to the Python dashboard. So before debugging, I frequently use this terminal to identify communication issues and confirm that the transmitter values are correct. Now let's go to the VSPE communication. Let me take a second. few seconds. Now, as you can see, I have paired the ports COM1 and COM2. Here also it's the connection or pairing of COM1 and COM2 is success. This is the VSPE. You can see through here we have connected everything. Now to explain, this COM1 is connected to PICSimLab workspace, and this COM2 port COM2 is connected to Python dashboard. VSPE stands for Virtual Serial Port Emulator. Its purpose is to create a virtual communication channel between PICSimLab and the Python dashboard. In my project, I created a virtual COM port pair. One COM port was connected to PICSimLab, while the other COM port was connected to the Python application. Whenever the STM32 transmitted UART data through PICSimLab, VSPE redirected the same data to the Python dashboard. This allowed both applications to communicate exactly like a real serial communication. That's connection. Okay. Now we are going to the final part, that's the Python dashboard. This is the Python dashboard. As you can see, now it's in the alarm state. The battery is 98.5%. The alarm is in critical condition. This is the bird eye view, ADAS bird eye view, and it shows all the values. It's blinking red color, so it's the alert that it's time the collision is going to happen. It shows the collision is going to happen. You can see this is the EV vehicle that ADAS is working on. This is the front obstacle. This is the right obstacle that's in 2 centimeter, and the left obstacle is in 13 centimeter. So this the part is very critical now. The speed is now 20 km per hour. So it's in constant condition. That's why this line is showing like this. Now we can wait. I'll show the simulation or the demo now. Wait for that. Wait. It's the Python dashboard developed for the project. It provides a graphical interface for monitoring the electric vehicle in real time. The dashboard receives UART data transmitted by STM32 and immediately updates all the vehicle parameters. It displays the battery, the digital speedometer, battery state of charge, remaining range, motor temperature, torque, alarm status, and the ADAS bird eye view. Whenever an obstacle is detected or a fault occurs, the dashboard changes the warning indicators accordingly. The dashboard makes the vehicle status much easier to understand compared to viewing only numerical values on a serial terminal. Let me show the final demonstration. Now I'll demonstrate the complete working of the project. Here the STM32 ID contains the embedded firmware that controls the entire system. Here it is. Okay, this is that. Let me show the main.c. This is it. Okay. Now PICSimLab then simulates the STM32 blue pill and all the required hardware components, and VSPE established the virtual serial connection between the simulator and the Python dashboard. As I change the potentiometer values, the obstacle positions in the PICSimLab, the STM32 and change. It will be transmitted through the UART. Now I will show you the demonstration. Okay, now this demonstrates the successful integration of embedded firmware, simulation software, and UART communication and graphical illustration into one complete EV ADAS system. Let me show you now. Um, Here it is. Now you can see, wait, I am now decreasing the acceleration, wait, front distance. I am increasing the front distance. Now here you can see the distance here also has increased. Obstacle is in distance now. It's moved very far distance. It's in 230 centimeter now. Low, so the front distance I am increasing more. Now it's in far very much distance with the with our vehicle. Let me increase the speed. It's in 20 kilometer speed now. I am applying brake. Now the distance has increased more. That's 239 and now 288 centimeter. Let me decrease the brake. You can see here the brake percentage is now at the 49%. So that's why the distance is constantly increasing. Now let me decrease the brake. And you can see now it has reduced to 5. Now, okay, wait, let me show you. Now as the front distance increases, the collision to the front obstacle is now not necessary, it's not occurring, so that's why the alert has gone, the red alert has gone. Now we are going to see now I am increasing the right distance, and you can see that the right obstacle has been to great distance, and now so the green light has got turned off. The green LED has turned off since the right side obstacle is not at the place of collision. Now increasing the obstacle is coming near, so here you can see the green light is blinking too. It's green, the green light has turned on. Okay, I'm moving now the right distance. Now let's talk about the left distance. I am increasing the left obstacle distance, and you can see there is no obstacle at the left. So the blue light has turned off. The LED has turned off. Now no alarm is there. Now okay, I have almost shown everything. Now you can see the torque is 148 Newton now. Newton meter. Acceleration is 99%, and the brake is only 4%. Motor temperature is also displayed. Alarm, there is no alarm now. This is the state of the battery. This is the charged battery now. There's no false now. The signal is on. Let me show you false. If I am increasing the temperature to very great distance, now look at this. The fault, that alarm, that the LED has been turned on, and you can see that fault in the fault rate. There's one fault. It's showing all fault. This is the speedometer. So this is the complete dashboard, AV ADAS dashboard. This is the bad eye view, and now we are at the end of our presentation. I have completed the demonstration too. So let me end our project. I want to conclude now. To conclude my presentation, this internship has been a very wonderful learning experience for me. It helped me understand how embedded systems are designed, developed, trusted, and integrated into real-world automotive applications. Throughout this project, I not only improved my technical knowledge but also developed patience, debugging skills, and confidence in solving practical engineering problems. Finally, I would like to express my sincere gratitude to my mentor, Miss Jayalakshmi Daniel, for her constant guidance, encouragement, and support throughout this internship. Her internship helped me overcome many challenges and complete this project successfully. I'd like to thank my internship organization, that's the Emertxe Information Technologies, my faculty members, and everyone who supported me during this journey. Thank you all for the valuable time and attention.